Hello viewers, welcome back to the course. So today I am going to take the last lecture of this first part of this course. So in the last class we have started with the Fourier transform, and then we have discussed the various properties of the Fourier transform. So from the last class I remember that if the function satisfy the sufficient conditions for the existence of the Fourier transform, then I know that for a function f t, or sometime I also write in the form of f x, my Fourier transform is given as f of t e raised to power minus I omega t dt, where omega is the angular frequency and it is any real number. So in that case, so this is my Fourier transform, and then from where there I can go back to my physical space by taking the inverse Fourier transformation. So that we have written like this one. So minus infinity to plus infinity, then the f hat omega e I omega t with respect to d omega. So this is the Fourier transformation, we call it f t, and this is the inverse Fourier transformation I dot f t. But if you see in the some books, they have taken the Fourier transform in this form also. So generally they take the Fourier transform in the some books like this one. So they have taken the Fourier transform like this, except 1 over under 2 pi, and then they take the inverse Fourier transform as 1 over 2 pi minus infinity to infinity f t e I omega t dt 2 pi. So some books follow this type of the expression for Fourier transform and the inverse Fourier transform, but in our case we are taking this one. So for the same value of the function you may have the different type of Fourier transform because of this factor 1 over under 2 pi. Now, so for example, like for example, in the previous class I have discussed that the Fourier transformation of the function, that is Dirac delta, so delta x minus a. So if you remember, then the Fourier transformation f of x minus a, it was from 1 over under 2 pi from minus infinity to infinity e raised to power minus omega t dt, and it is coming 1 under 2 pi e raised to power minus I omega a. So that was the Fourier transformation for the Dirac delta function. Now suppose I take for a is equal to 0. So in that case my Fourier transformation of the delta function will be 1 over under 2 pi and into 1. So in this case this will be under 2 pi. But generally in some books also they take that the Fourier transformation of Dirac delta function is 1, because they are using sometime this type of expression for that. So in that case value will be 1, but here we are using this one, so that is why the value 1 over under 2 pi is coming. So if I suppose I take this value, then you can see from here that if you remember from the Laplace transformation, then the Laplace transformation and Fourier transformation for Dirac delta function is 1. So in this case both the transformation are coming 1. So that was the Fourier transformation for the Dirac delta function, and then we can have a different type of functions. So in the previous class also, then we have discussed the Fourier transformation for the function f t is equal to e raised to power minus a t into unit step function when t is positive and 0 when t is negative or equal to 0. So, that was the we have discussed with that, and in this case if I take the Fourier transformation f of f t, my f t dt, then we have seen that this is equal to 1 over under 2 pi into 1 over a plus I omega. So, these factors is multiplied by this one. Okay. So, this is my Fourier transformation. And what will be the inverse of Fourier transformation? So, suppose this is my f of omega, and now I want to take the inverse of this one. So, inverse of this one will be one over a plus I omega is equal to, that will be always equal to e raised to power minus a t u naught t when t is at 0 otherwise. So, that is the function we have. So, that is the inverse Fourier transformation for the same function. Now, we can have another function. Then also we have discussed that suppose I take the another function, my f t is equal to e raised to power minus a mod t. So, in this case this will be equal to e raised to power minus a t when t is greater than 0 and e raised to power a t when t will be less than 0. So, in this case also if I take the Fourier transformation of my function f t, then this will be 1 over under 2 pi, and then I will split my integral from minus infinity to 0, it will be e a t e minus I omega t dt plus, and then from 0 to infinity it will be e minus a t minus omega t dt. So, if you further solve this one, so this will be, so it can be written as a t. So, I can write from here, this will can be written as a minus I omega t. So, this one can be written like this plus e raised to power minus, I can take common. So, a plus I omega t dt, and if I further solve this equation, so the integral will be e raised to power a minus omega over a minus I omega plus a plus I omega t divided minus a plus I omega. So, this will be the expression for that. So, which further can be solved. Now, I will get a minus I omega, and the limit, I have to put the limit from here. So, in this case, so this expression, so from here I can write that this is equal to 1 over pi e a minus I omega from minus infinity to 0, that was the limit, minus a plus over a plus I omega. So, this will be from from 0 to infinity. And now this expression we know that the limit t tends to minus infinity e a minus I omega t, that will be 0, and the limit t tends to infinity e raised to minus a minus omega t, a plus omega t, that will be 0, because this is the decay function, and when t tends to minus infinity this value will be 1 over infinity and that will be 0. So, in this case this will be 0. So, from here if I solve it further, so I will get this expression 1 under root 2 pi 2a over a square over omega square. So, if I solve further from here I will get this value. So, from here I can say that the f of e raised to power minus a mod t will be equal to 1 over under 2 pi 2a over omega square. And from here if I want to take the f inverse, the inverse Fourier transformation of this expression, then it will be minus a mod t. So, that will be the inverse Fourier transformation for the Fourier transformation of the function e raised to power minus a t. So, these are the few Fourier transformation of few functions. Then we define some properties. Of the Fourier transformation. So, now the few properties, linearity property and the Fourier transformation of the derivative we have already done. So, today I will start with the third one, the third property, and that is called the shifting on t axis. So, it is same as the shifting theorem what we have discussed in the Laplace transformation. So, shifting on t axis. So, in this case if I take the Laplace transformation Fourier transformation of the function f t and we write as f hat omega, and suppose t naught is any real number, then f of t minus t naught. So, I just do the shifting in terms of t, then this value will be equal to f hat omega e raised to power minus I omega t naught. So, in this case there is no need to solve the Fourier transformation again, we can use this property. So, the proof for this one is I want to find the Fourier transformation of the function f t minus t naught. So, this is 1 over under root 2 pi from minus infinity to infinity f of t minus t naught e minus I omega t dt. Now, I change my parameter. So, I take this transformation, I take t minus t naught is equal to some tau. So, from here I will get t naught plus tau, and also I get from here that the dt will be d tau, and when the t will be minus infinity, tau will be also minus infinity. When t is infinity, then the tau will be infinity. So, from here if I apply this transformation, so I will get 1 over under 2 pi f of tau. So, this is the tau we have taken, e minus I omega, and instead of t I put t naught plus tau and d tau. So, from here I can take this part common. So, because I am taking the integration with respect to tau now, so this is a constant. So, I can take this one outside, I will get minus I omega t naught divided by 100 pi from minus infinity to infinity deta. And if you remember, then this is the Fourier transformation of the function f. So, from here I can write that this is equal to e minus I omega t naught. So, that is the Fourier transformation of the function which is shifted on t axis by t naught. So, let us do one example. So, let us take the example. So, suppose I want to take the inverse Fourier transformation of the function. So, let us define. So, let us solve so f of inverse of e 4 I omega divided by 3 plus I omega 100 pi. So, this one I want to solve. So, from here if you see, then I have to compare these functions with the shifting theorem, because here I am getting e raised to power something. So, that is also here, and f the Fourier transformation of the function f hat omega is somewhere here. So, from here I can see that. So, this one I can written as 1 over 100 pi 3 plus I omega, I take separate and I write here 4 I omega, and then I will compare here with this value. So, from here I can say that I am getting my f omega is equal to this one 3 plus I omega, and from here I can say that T naught will be minus 4, because T naught is minus 4. So, from here now my f omega is 1 over 3 plus I omega. So, that is equal to, if you remember, so this will be equal to e raised to power minus a is 3 t into u naught t. So, that is my expression for which the Fourier transformation is this one, because this one we have solved here in the, so this one. So, from here I apply my shifting theorem. So, using shifting theorem, I can write that in this case the f inverse of f hat omega into e raised to power 4 I omega will be. So, using this property I will write that this will be equal to the f of t minus t naught. So, it will be 4. So, from here I can write that the answer will be f t plus 4, and this is equal to e raised to power minus 3 t plus 4 u naught t plus 4. So, from here I can write this one as e raised to power minus 3 t plus 4. So, now this quantity is u naught, I can write as, from here I can add u naught t plus 4 will be 1 when t plus 4 is positive, 0 otherwise. So, from here I can say that this is equal to 1 when t is greater than minus 4 and 0 otherwise. So, from here I can say that this is equal to the function u minus 4 t. So, this function can be written like this one, and which further can be written as e raised to power minus 3 t plus 4 when t is greater than minus 4 and 0 otherwise. So, that is the inverse Fourier transformation for this function, and the answer is this one. So, this is the answer for that. So, now we can take the another one, the fourth property, and that is called another shifting theorem. So, shifting in frequency. So, in this case, if the Fourier transformation of f t is f hat omega, and let us we choose omega naught is any real number, then if I take f of e I omega naught t f t. So, I want to take the Fourier transformation of the function multiplied by this one. So, this will be equal to f hat omega minus omega naught. So, this is we have done the shifting in terms of omega. So, the proof is straightforward. Now, I have given by this. So, I want to find the Fourier transformation for the function e I omega naught t f t. So, by the definition I will write like this. So, my f t is there, e I omega naught t e minus I omega t dt. So, from here I can write this expression from minus infinity to infinity f t e, and from here this I can take common. So, I can take I common and t common. So, from here I can write minus omega minus omega naught I t dt, because it will be e raised to power minus I omega minus omega I t minus omega I t, and this negative will be go inside. So, it will be this one. So, from here, so if you remember this one, so this is same as the Fourier transformation of the function except this factor. So, from here I can add that this should be equal to f hat omega minus omega naught. So, that is the proof of this one. So, that is called the shifting in the frequency. Now, so after solving this problem, so let us solve few differential equations. So, in this case I want to solve some ordinary differential equation with the help of Fourier transformation. So, let us take example 1. So, one example I have taken I think in the previous class. So, the same I just take the same type of example. So, let us take this one, dy by dt minus 4y is equal to e raised to power minus 4t u naught t, where t is defined from minus infinity to infinity. So, one thing you should keep in mind that in this case, suppose I want to solve by the Fourier transformation. So, the question is that solve this one, solve this using Fourier transform. So, that is the question. So, and we know that the Fourier transformation can be applied only when the function satisfy some conditions, that the function is piecewise continuous in the finite interval, it is absolutely integrable. So, in this case we assume that the y t satisfy all the sufficient condition for the existence of the Fourier transforms. So, let us take the Fourier transformation. So, apply Fourier transformation both side. Now, from here I can write that f of, so this can be written as y dash, basically I am taking minus f of 4y is equal to Fourier transformation of e raised to power minus 4t u naught t, and this is equal to, I know that this is omega. So, let us take that f of y t is this one. So, from I can write that this will be equal to this one minus 4 times, and this one will be equal to 1 over a is 4. So, 4 plus I omega. So, we know that this is 4 equal multiply. So, if you remember, then f of e minus 4t u naught t is 1 over under 2 pi over 4 plus I omega. But whenever we are solving the differential equation, we ignore this factor, because on the left side also we are taking the Fourier transformation, on the right hand side also we are taking the Fourier transformation, and we consider that this factor 1 by under root 2 pi got cancelled. So, whenever we are solving the for the differential equation, we generally ignore this factor. It is just the multiplication by this sum factor. So, in this case I will take my Fourier transformation for the function as this only. Now, if I go further, and this will be equal to I omega minus 4 is equal to 1 over 4 plus I omega. From here I can write my 4 plus I omega, and then I omega minus 4. From minus 1 I can write this as 4 plus I omega and 4 minus I omega. So, from here I can write this as 16 plus omega square. So, this is my Fourier transformation. Now, I have my solution in the yt. So, now I have to take the inverse Fourier transformation. So, inverse Fourier transformation yt will be f of inverse of this function minus 1 16 plus omega square. And if you remember, we have taken the Fourier transformation of this function e minus a mod t. It was coming 2a over a square plus omega square, 1 by under 2 pi. So, that is I am ignoring. If you just remember this one. So, this is, so that is the Fourier transformation I am going to use. Now, from here I can write that. So, suppose my Fourier transformation is this one. So, this expression can be written as minus. So, 2a I will take. So, in this case my a is 4. So, a is 4. So, I will get my 2a f of inverse 2a a square plus omega square, where a is 4. So, it will be 8a by 16 plus omega square, and this one I have taken the factor outside. So, from here I can write that my yt will be minus 1 over 8, and this one I can write as e raised to power minus a is 4 mod t, which can further be written as, so this is equal to minus 1 by 8 e raised to power minus 4t when t is greater than 0, and this will be minus 8 e 4t when t is less than 0. Now, from here I just want to, so that is the solution. So, you will get the solution in the terms of piecewise function. Now, from here I just want to verify that, from here you can verify that if I take the limit, if I define this function, then this function is a decay function and it is absolutely integrable. So, I can take the integration of this function and that will be finite, the absolute value. And also I want to check that what will happen if I take limit t tends to infinity. So, if I take t tends to infinity y t, so this will be limit t tends to infinity minus 1 by 8 e raised to power minus 4t, and that will be 0. Also, if I take limit t tends to minus infinity y t, so I will take this limit t tends to infinity minus 8 e 4t. So, t tends to minus infinity, this is minus infinity. So, then its value will be 0. So, these two properties are satisfied. So, from here whenever we are solving any of the differential equation ODE with the help of Fourier transformation, it is understood that my function satisfy this condition. Okay. So, that is the solution for the first order ODE. So, let us take another example. So, after solving the ODE, I take the second order ODE. So, solve using Fourier transform. I will take the second order ODE y double dash t plus 6 y dash t plus 5 y, that is a function of t, is equal to delta t. So, this one I am defining, and t is belongs to the real line. So, if you see that I have taken, so this is my differential operator. So, L of y t is equal to delta t, and this one I want to solve. So, if you remember that whenever we have a right hand side function as a delta function, and the solution of this equation become the green function. So, basically here I want to find the green function of this differential operator. So, this is my differential operator L y L. So, I want to take the L y t to find out the green functions. So, from here, and in this case I know that my function y t is a well defined function satisfying all the sufficient condition, and also I will be 0. So, this is understood that I am taking this one, because this is not given any of the differential equation, but whenever it is being told to solve by the Fourier transformation, then this is already satisfied. Now, solution. So, let us take the apply Fourier transformation to the equation 1 both side. So, in that case I will get the f of y dash t double dash t plus 6 of f y dash t plus 5 of f y is equal to f. So, this one I have taken. Now, from here I know that this will be equal to, so I am considering here that f of y t is f, instead of f I just take y omega. So, from here I can write that this will be equal to I omega square, that we already know. So, this will be equal to this plus 6 times I omega plus 5 times is equal to, this is equal to 1. So, that is the Fourier transformation, the drag delta function. So, that is a 1. So, from here I can write that this will be can be written as, so I take y omega common. So, this can be written as minus omega square plus 6 I omega plus 5 is equal to 1. So, this one I can further write, and I can take minus 1 outside. So, this will become omega square minus 6 I omega minus 5. Which can further be written as, so this one I will just take the factorization of this. So, I can write this as omega minus I. So, this one minus 5 I omega minus I. So, this can be written as, because when it will be omega square minus omega I minus 5 omega I. So, it will be 6 omega I and minus 5 I into I square. So, it will be plus and I square. So, it will be minus 5. So, from here I can write, then this can be factorized. So, factor would be omega minus 5 I and omega minus I. So, now I want to take the inverse Fourier transformation. So, I want my solution in terms of yt. So, this will be f inverse of minus 1 into omega minus I. So, this one I want to take the inverse Fourier transformation. So, if you remember, the same thing used to happen in the Laplace transformation. So, we have to simplify this one by taking the partial fraction. So, this one I can be written as, if I do the taking the partial fraction. So, further solving this one, this can be written as 1 over. So, if I will take the partial fraction, it will becomes 1, this will become 1 over 4 I omega minus 5 I, taking the minus sign outside, plus minus 1 over omega minus I. So, this one be equal to so this one will be minus over 4 I, because if you take the LCM of this, it will be omega minus 5 I omega minus I, then it will be omega minus I minus omega plus 5 I. So, this will cancel out, this will be 4 I and 4 I will cancel out and we will get the same value. Okay. So, from here, so that is verified now. So, from here I can write that this will be equal to minus of f inverse, and this 4 I can take inside. So, it will be, so I can take just 4 here. So, this one can be written as, I am just taking the I inside, it will be I omega plus 5 minus I omega minus I square. So, it will be plus. So, this is minus 1 by 4 and this is satisfying the linearity property. So, this is equal to 5 plus I omega plus minus, because I know that it satisfies the linearity property. So, I can take this as 1 plus I omega. So, which can further be solved and can, because now I have to take the inverse Fourier transformation of this factor. So, I remember that this is equal to e raised to power minus 5t u naught t, where unit is the unit step function, minus e minus t u naught t. So, that is the inverse Fourier transformation. which can be written in the form of a piecewise function. So, this become equal to, the solution become minus 1 by 4 e minus 5 t minus e minus t when t is greater than 0, and otherwise this will be 0 otherwise, or I can say here that this is equal to when t is less than 0. So, that is your solution, and when I put t equal to 0 in this case, so this value will be 1, this value will be 1. So, it will be this factor. So, maybe I can take equal to sign also here. It depends upon that how you are defining your unit step function. So, that is my green functions for my given differential operator, and the value of the green function is, so it is splitting at the 0. So, this is my solution of the, that is my solution of the equation. So, this is the solution, and also it satisfying that when t tends to infinity, I will take this will go to 0, and t is less tending to minus infinity, this is 0. So, based on this type of equation, we can find the solution, or we can solve the given differential equation with the Fourier transformation. So, let us take another example, a little bit the same type of second order differential equation. So, let us solve another example, solve using Fourier transformation y double dash t plus 3 y dash t plus 2 y t is equal to e raised to power minus 3 t u naught, okay, where t belongs to real line, and as I told you, it is understood that y plus minus infinity will be 0, and satisfying all the sufficient condition for the Fourier transformation. Now, solution that, so call it equation number 2, apply Fourier transformation to equation 2 both sides. Earlier I have taken the equation number 1, yeah. So, this is the equation 2 I am. So, I am applying the Fourier transformation to the equation number 2 both sides. Now, the same way I can find, so let my Fourier transformation for my function f of y t is y hat t, or y hat omega. So, from here I can write directly, I can write that this will be equal to I omega square plus 3 I omega y hat omega plus 2 y hat omega is equal to, so this is equal to 1 over a is 3 plus I omega. Now, if I solve further, so this will be equal to y hat omega, it will be minus omega square plus 3 I omega plus 2 is equal to 1 over 3 plus I omega. So, which can be further solved. So, from here I can write this function as one over 3 plus I omega, and I take the minus sign here. So, it will be omega square minus 3 I omega minus 2, which can be further factorized. So, it becomes 3 plus I omega, and this one I can write the factor form. So, it will be omega minus I omega minus 2i, because when omega square this will be omega minus 2i and minus I omega minus 3i omega and minus I into minus 2. So, it will be minus 2. So, I can get these factors. Now, I have to take, so now apply inverse Fourier transformation, and from there my solution yt can be written as f of inverse of this factor minus 1 3 plus I omega omega minus I omega minus 2i. So, now the same way I can apply my using the help of partial fractions, I can simplify this function. So, if I take the partial fraction of this expression, then I will get this value. So, this is equal to minus 1 over 2 plus I omega. So, this is coming plus 1 over 2 1 plus I omega and 1 over 2 3 plus I omega, because here we have multiplied by I, because we want to take. So, here I am taking with the I. So, it is 2 plus 3i, okay, 1 plus I, 1 plus this one. So, in this case I just multiply by I. So, I will get 1 plus omega I. Here also I multiply by I will get this one. So, these factors are, because I know that I want to take the Fourier inverse, and Fourier inverse is applicable only for this form whenever I have this form a plus I omega. So, if I solve this further, taking the LCM, I should get the same value. So, this is the factors we are getting, and now I apply my inverse Fourier transformation. So, from here I can write using the linearity property, I can split this into this form 1 plus I omega plus I omega. So, this is equal to minus E minus 2t u naught t plus 1 over 2 e raised to power minus t, because a is 1 here, u naught t plus 1 over 2 e minus 3t u naught t. So, that will be my solution, which can be written as, it will be equal to minus 2t plus half e minus t plus half e minus 3t, and this t will be greater than or equal to 0 and 0 when t is less than 0. So, this is my function and that is the solution. So, this is also given in the piecewise form, and when I t tends to infinity, this factor will vanish to 0, and when t tends to minus infinity, this vanishes to 0. So, that is the solution of the differential equation. So, the today class we have discussed that the various application of the Fourier transformation and the inverse Fourier transformation to solving different type of first order differential ODE and the second order ODE. So, and as I told you that today is the last class for the first part of the course of this course. So, I hope that you enjoyed this course. Good luck for this course. Thank you very much.